Hi everyone, my name is Vikram, and my project for this semester was using machine learning to detect cache side channel attacks. I'll just say ahead of time that I'm a bit under the weather, so if my voice is hoarse or I have to take pauses, it's likely because of that. Anyways, I'll get started. So as an introduction to the project, it's based on one of the seed ideas that was provided called Your Cache was My Cache. The overarching goal is to create a defense against cache-based side channel attacks, which I'll explain later. And more specifically, the goal is to use machine learning to build a classifier which uses hardware performance counters to classify four of these cache-based sidechain attacks, which I'll also cover. So, what are cache sidechain attacks? These are attacks which exploit memory access patterns in the cache to extract sensitive information from the victim. In terms of threat model, there are some things you have to assume. First is that the attacker and victim share the same cache and CPU, because these sorts of attacks work by flushing or evicting the cache, which I'll go into more later. Uh, the attackers may also know the associativity of the cache or how it's mapped. That's for particular attacks, by the way, uh, and can measure timings precisely. The attackers can also, they don't really need root privilege. They only have to use user space or sandbox environments. In terms of the data that could be exploited by an attack like this includes things like cryptographic keys, uh, and then also like user behaviors like keystrokes or maybe password length or program behaviors, particular instructions, things of that nature. So as you can imagine, the data that you're looking at can be pretty sensitive, which makes this project so important. I'll provide a brief refresher on cache lines. The CPU cache is composed of multiple levels. You have like L1, which is the fastest, all the way down to like L3. Each of these levels is composed of cache sets, and each set is composed of a certain number of cache lines. The number of cache lines being its associativity, which I mentioned earlier, something the attacker might need to know. Thus, the cache line is the smallest unit of memory in the CPU cache. There are things you could do with a cache line, such as flushing it. Flushing a cache line means removing it from every cache level, so it has to be fetched from memory. You can also evict the cache line, which is similar to removing it from memory, but instead of explicitly doing it, you're indirectly doing it by accessing memory addresses mapped to the same cache set. The way it works is that a cache set can only have a certain number of cache lines at a particular time. So if you access other memory addresses enough, uh, the cache line you're targeting will be ejected or evicted. It's the right term. Now I'll go a bit more in depth on specific attacks. So first off, one attack is flush and reload. This will flush specific cache lines to detect if a victim has accessed them. That way, if the access is slow, that means the victim hasn't. If it's fast, that means the victim has. So you can determine particular data using that. This requires having a shared memory, and then also it uses an instruction called CL flush, which can be logged by certain programs. There's also another attack called prime and probe. In this, an attacker will prime, or rather like fill a cache set with their own data. Then once a victim executes some command, the attacker will probe their data to see how it's changed. Uh, there's no shared memory in this, but the attacker has to know how the cache sets are mapped to figure out like how their data is being changed and to infer how the victim is working with their data. The third attack is called the victim reload. This is similar to flush and reload, but instead of flushing the cache, it uses evictions, which you'll recall is like using addresses mapped to the same cache set to indirectly remove a cache line. This again requires shared memory and an ability to identify congruent addresses, that is, addresses which would be mapped to the same cache set. Then finally, there's flush and flush. This is a bit different. It actually measures the execution time of CL flush itself, which you'll recall is the instruction used in flush and reload. This again requires shared memory, but it has a much more minimal footprint than any of the other instructions because it can't really be logged. There are multiple defense strategies you can employ. Sorry, give me 1 second. There's multiple defensive strategies you could employ against these sorts of attacks. These include things like data obfuscation or noise injection, which would affect the attacker's ability to observe like meaningful patterns in timing. You could like add random delays, or you could access like decoy addresses, things like that. There's also context switching, where you're uh, I guess like changing the cache state between different processes. So like when you switch between one process and another, you flush the shared resources. So like a cache or a TLB. So the attackers can't look at the state in transition. Another tactic is to randomize the cache indexing. What this means is just changing how it's mapped to make the patterns unpredictable for the attacker. You could use dynamic binary execution, which means that you actually obfuscate the binary at runtime to make them less predictable. Then finally, you could use hardware performance counters, which allows you to monitor hardware level behavior to detect cache attacks. And this is the focus of this project. We're using machine learning, which should be good at generalizing the patterns garnered by malicious programs versus benign programs. As for how this is implemented, for the hardware, I benchmark the attacks and the benign programs on Ubuntu with WSL. As for the attacks, I'm using an existing implementation from a library called Armageddon. You can see right here. It's for cache attacks on mobile devices, but they actually provide a library which allows you to execute and benchmark cross-platform cache attacks on the x86 architecture. And conveniently, it includes all of the 4 attacks which are required for the seed idea, which makes it the perfect place to work off of. As for data, we use perf. Sorry. We use perf, which is a hardware performance counter, and also pandas for data ingestion and feature engineering. As for the model and visualization for the machine learning, we use scikit-learn, and then for the visualization, matplotlib and Seaborn. So now I'll move into the dataset collection. The goal of this, if you'll recall, is to record hardware performance counter values. If you look at the screenshot on the right, that is the output of running perf list. That'll give us a list of predefined events that we can use and benchmark with. What I did was I chose a subset of these events and then ran them for the malignant entries, like the 4 attacks, as well as a set of benign programs that I defined. And then this eventually resulted in a balanced data set of 64 malignant entries, so 16 samples per attack, and then 64 benign entries. I also did some feature selection and engineering, which I'll get into. I decided to start with a small set to avoid the effects of noise, which is certainly more present in simpler models, like, let's say, like logistic regression. The first one is branch instructions and misses. This is because attacks will usually have a very predictable control flow. Second is cache references and cache misses. This is because attacks will often cause more cache misses than a benign workload. The third is cycles and instructions. Attacks will often do less useful work per cycle, which just means that it'll have higher cycles per instruction. And then finally, 2 features which have to do with the L1 cache, because due to things like evicting and reloading, the access patterns for the L1 cache could be different for attacks. I normalize all these features. So instead of having instructions and misses, I have like miss rate, for example. The reason being that there could be some variability in between runs, and this allows everything to be a lot more reflective of the actual efficiency of the programs. And then as for determining the feature importance, I use ML to do that. You'll see that in a Jupyter notebook later. So now I will get into the demo. Just give me 1 second. Okay, I'm going to go ahead and open up instance of WSL. Okay. So you can see my workspace. I go into Armageddon and then libflush, which is the library I'm using. I'm going to start by just going into the folder which contains the binary I'm using, and then there's this sample command which I just kept here. What this is doing is it's running the flush reload command, and it's getting the cycles, instructions, cache misses, and it's going to run perf on that. So you can see what's here is like the actual output of the program, but you can see the performance counter values for just running flush reload, like right here, which is great, which means that we can like benchmark any attack that we really want to. If I want to, I could like change this to be like flush and flush, and you can see I get a different output. Okay, so now I'll show what I did for dataset collection. So look into file, collect perf dataset. You can see I have all of the events that I'm gathering, which I discussed earlier. And then you can also see there's 16 samples for each attack, and then there's 4 samples for each benign program. How I picked the benign programs was kind of arbitrary. I had to look up a lot of examples to see what I could use, but I tried to use like many different workloads to get as robust of a spread as possible. You can see I have like IO bound operations like cat and grep, CPU bound ones like, for example, this Python command which just runs a massive loop. Memory bound ones like sort. This code just runs everything and converts it to a pandas data frame. Now I'm going to show the first notebook. Okay, for that. Okay. I'm going to go ahead and open all of these right now. Just give me 1 second. Okay, great. So I'll start with classify perf. This is the first notebook that I worked with. I ingest the data set. You can see I'm normalizing the features by their rates. And then I start with this feature correlation matrix, which does a good way of telling you which features will create like redundant information. As you can see, there's actually a fair amount of redundant information between things like cycles and instructions and misses. But for the engineered features, it's closer to blue, which means that the features are less redundant and we can get more information. I then plot the distribution just because I wanted to see how different the spread of these features are for malignant versus benign programs. You can see here there's a fairly different pattern and spread, especially for the miss rate and then the L1 miss rate. So I normalize the features. I do some like PCA reduction, like visualization. You can see here that there are these distinct clusters, and also the data is like pretty easily linearly separable, which is a great sign. As for the model, I'm using logistic regression. Logistic regression, I mean, the way logistic regression works is that it does like binary classification. It's also like very linear. I'm kind of blanking. If I recall correctly, it uses like log odds to model like the probability of whatever classes you want. In this case, there are 2 classes like malignant and benign, but it's just about as simple of a model as you can make. So it's very lightweight, which is kind of was like one of the goals for this, was to like work my way up in terms of complexity. So if we evaluate it, you can see actually like this simple model performs surprisingly well on our test data. Like the accuracy is 100%, which is pretty surprising. I also conduct cross-fold validation, which should decrease the accuracy, but since it's showing 100%, that means everything's being perfectly modeled. I decided to look into the features that the regression weights as the most important, you can see that the cache miss rate is weighted very heavily, and then so is the branch miss rate, which makes a lot of sense because those are very central to how these attacks work. You can also see I made some box plots which show you the spread of these attacks. You can see like for cache miss rate, for example, there's a really big difference in the spread of malignant versus benign. Same with the branch miss rate. Uh, I mean, and I wrote here, by the way, it kind of makes sense the way that these are modeled. Like the cache miss rate being so high makes a lot of sense because these attacks are intentionally generating cache misses to collect info. And for the branch miss rate also makes sense because these attacks will have much like tighter loops and not a lot of conditional logic, which would cause a lot more branch misses. Because logistic regression can be sensitive to noise, I removed those features and then I rewrote the program. You can see just like similar accuracy, even though now it's only using the cache miss rate and branch miss rate. And then I save the model. Okay, that's that. And then I also made, I'm just gonna shut this down. Okay, so I also made this utility which allows you to classify these at runtime. Oh, right. 1 second. I to activate my virtual environment. So I run this script, and then if I want, I could type in the name of one of these programs, and you can see the classifier that I saved earlier actually predicts it as malignant. I could do the same with a benign program, cat. You can see it's similar there. It's kind of cool. Let me try like evict. Yeah. You can see the confidence is like lower for this one. Which means that the model isn't perfect, but it does surprisingly well for how simple it is. Okay. So the classifier works pretty well, and you could call that the end of the project, but I wanted to do some more. So I asked myself, like, how could I, extend on the project? And I came up with 3 things. First of all, can we improve the robustness of the data set? Second of all, is it possible to modify the cache attacks to fool our classifier? So like a sort of like evasive strategy. And third, if those evasive tactics are successful, can we defend against them somehow? So I started with dataset collection. One of the things I did was I added a bunch of variable parameters. Sorry, my voice. I added a bunch of variable parameters. These include random address offset, sleep, etc. I also added hybrid behaviors. These are where I combine malignant data as well as or malignant programs as well as benign programs to try and like obfuscate all of those like bad behaviors, I guess. And then another thing I do is I increase the number of samples, in particular from 128 to 512. So I'll go back and show what I did for that. So back here, the first thing I did was going here. You can see that there are other versions of the main.c file. So I made a different version. I had to change a lot to make that happen, actually. This file, for example, you can see I have particular flags. Give me like 1 second. Right. I have particular flags that I'm using, which are a little different from the previous script. So some of note are like the number of rounds, like the R flag, which determines like the amount of loop runs for the attack. So you can simulate like a much larger attack if you want. You could also change the batch value, which varies the number of addresses that are being flushed. You could add a random offset in memory, which creates like variations in like how the memory is used. You can add an arbitrary amount of sleep between loops. I don't think there's anything else I'm missing. Yeah, like the hybrid flag, of course. Uh, there are also things I do in like a separate script, which is like, for example, I like bind to different CPU cores, which like avoids issues with like cache locality if it is an issue. Um, and I think that's pretty much it, actually. You can see like, for example, here, this loop, I'm like injecting arbitrary noise, or I'm opening a benign process, or like using sleep, for example. That's all great. Uh, this script, which collects all of the new data, you can see like some web programs being ran. Actually, not much to show here, to be honest, but you can see like, for example, binding to like different CPU cores here. On to the next Jupyter notebook. This is creating the more robust data set. Um, Something that you should immediately note here is that if you look at the distributions, it's a lot more similar than it was before, right? You can see a lot more overlap between the patterns for all of the features that have been measured. And then when you conduct PCA, you can see that while the clusters are kind of clean, some of them kind of overlap with the other classes, which could be challenging for a model. So I use the same model. I don't even bother saving it because it's so lightweight. You can see that the accuracy actually drops from 100% to 93%, with a lot of benign programs being misclassified as malignant. Uh, I mean, most of the malignant programs that are being misclassified are hybrid programs as well, which shows that that defense or that obfuscation works. You can see lower cross-validation values as well. And then also something interesting is that the relevant features kind of change. So like now the things that are weighted are cycles per instruction and then the L1 miss rate. I decided to try and use more robust models than before. So for instance, I use a support vector machine, which is a model which tries to, I guess, maximize like, it finds like a hyperplane, which maximizes the decision boundary between particular sets of classes. Here I'm using a polynomial kernel, which means that it's not just trying to find like a linear split. It's finding something that can be projected in a higher dimension. You can see that already increases our accuracy significantly to 97%. I also use random forest classifier. Random forest classifier is an ensemble model. It combines a bunch of simple models known as decision trees, which provide this sort of like decision-making process as to like uh, which sets of features being what values dictates a particular class. Uh, what random forest does is it takes many of those decision trees and then aggregates them together in a process known as bagging. And then it will use like majority consensus to determine a particular classification. Uh, the end result of this being that it's resistant to noise and it's also very robust. So you can see an example of that here. It classifies everything correctly with still pretty high. I mean, this is a bit lower, but still relatively high success rate. So you can see here, I also plot the feature importance of the four features. In this case, it seems like everything's kind of important, but surprisingly, branch miss rate is actually pretty unimportant because we've been able to obfuscate it quite well. Uh, After this, I go into evasive strategies, which I'll cover in another slide. But you can see here, a lot of this is very similar. The major things that we need to work on for evasion is lowering the cache miss rate and then also the cycles per instruction. So evasive strategies. The goal of this is to determine if an attacker could trick the model we made. I do a couple things for that. I implement feature mimicry, which adds like benign cache loads and branch variation to simulate a benign program. I also create more hybrid attacks, and then I add counter noise, which will run pretty compute heavy loads to simulate like higher branch usage. Okay, so um, I'm starting to run out of time. So I will really briefly show the evasive version I implemented. You can see like additional features here, like mimicry and then counter noise. Not much to show, to be honest. Uh, there's also a script to collect the data. I'll just skip to the notebook actually. Load the model, use the same feature set, and then you can see uh, about 12.5% of the examples pass. Only like 5 out of 40, which isn't a lot, but given the sensitivity of the data, I still think it's important to lower this. So after doing that, I decided to look at defenses against evasive strategies. There are a couple. So like increasing the model robustness, like increasing the number of features, or increasing the variability of the data set, increasing like the number of samples you're using, or using like a temporal model. I decided to focus on the number of features. So go back to that. I decided to massively increase the amount of features I was using. So I'm using things like TLB miss rate, migration rate, switch rate, minor fault rate, just anything that I thought could be relevant to memory or cache access, or like context switching, stuff like that. After doing that, you can see here for the new features, there's a pretty different spread and a bit more separability. Once I use random forest, I actually get an accuracy of 100% once again. But what you should note is that the cross-validation scores are much higher than from before, which means that there's a clear improvement. You can see that the most important here is migration rate, then TLB miss rate, cache miss rate, and then switch rate, which I'll get into why it makes sense that those are so important. I don't really need to prune for features like I did with logistic regression because random forests are resistant to noise. So I just go ahead, I look at all of the different spreads, I test against the evasive data from earlier. And as you can see, now none are detected as benign, which means that the evasive strategies are passing the more robust model that I've implemented. Okay, so why are these features important? It actually makes a lot of sense. The migration rate being distinguishing makes sense because attacks will have tighter loops, which means that there's more frequent rescheduling and migration, so higher migration rate. TLB miss rate makes sense because a lot of these attacks touch non-contiguous memory, so there's more page table locks and more TLB misses. Cache miss rate, it kind of makes sense because attacks will be working across the cache because of like flushing, so they have worse cache locality. And then context switch rate makes a lot of sense because sometimes attacks will yield intentionally by like sleeping, for example. We might have also like contributed to that with the sleep flag, but I think in terms of like what I was trying to do with like I guess making the data or giving our model a harder time, then it was still pretty good. So in conclusion, for this project, I simulated cache-based side channel attacks using an existing library, Armageddon and libflush. I recorded hardware performance counters for both malignant and benign programs, I chose. I created an initial machine learning model, which was fairly successful, but then deciding to improve on it, I increased the robustness of the data set and explored evasive strategies. Finally, I used those findings to increase the set of features and inform an additional model, which was much higher accuracy. As for future work in the space, I'd have two recommendations. One would be building a real-time classifier or a system D service, which could run in the background. And because random forests are pretty lightweight, easily like flag programs as they're running, like malignant programs. I was trying to do this, but I kind of ran out of time too. Another one would be using temporal data to detect malicious time series patterns. I decided not to focus on this because my model performs so well, I just didn't really see the need for it. But maybe there is a use case where you could use like an LSTM or an RNN or some sort of architecture that looks at like time series analysis, ideally something lightweight. But maybe there's something more robust to be garnered from there. I'm not really sure. But yeah, that's pretty much it. Thank you for listening.